So yeah, so in my first lecture I was just trying to state. So I tried to state the Gross Zagier for for modular curve, and then for Shimura curve, and then I moved to sort of higher dimensional Shimura variety. So generalization in the context of arithmetic GGP Gann-Gross conjecture. So the setting was I had a quadratic. So now it will be a CM extension, quadratic. So I have a G being unitary group, certain. So Hermitian space of dimension n, n and n minus 1. So then I have a subgroup embed, so some diagonal embedding. So I look at the Shimura varieties, the sub Shimura varieties. So with a specific signature condition. So the sign was basically V at Archimedean place n minus 1 1. Just to remind you, 0. So definite at all except one place. So So I used a child group in the first lecture, but maybe it's actually things become unconditional if you work with say periodic Abel Jacobi map. So let me actually sort of record it a little bit the conjectures I formulate in the end of the first talk, but in a new setting. I mean, it's almost the same except you replace the child group by the periodic. So okay, let's call it the periodic version of arithmetic GGP conjecture. So we do this very quickly. So here I have the Shimura varieties. So attached to G. So maybe I should have put some level, but I will be kind of. So I will consider all possible level here. So maybe I will just forget sometimes, to mention the level, but you should take the level structure. So I will. Right. So the child group of cohomology trivial cycle. So at least if I put a level structure here, so of certain codimension. So here is codimension n minus 1. So this goes to the cohomology trivial part. So this was the kernel of the cycle class map. So there is a periodic Abel Jacobi map. So this goes to H1. So the Shimura variety defined over spec of quadratic extension of F. So there is a map goes to the first Galois cohomology of twice of degree, so 2n minus 1. Okay, minus 1. So of Shimura variety. Okay, here I should go to the algebra closure. So this is the periodic cohomology with periodic coefficient. So go to algebra closure. So f prime bar, okay, which becomes very awkward to write. I'm sorry. So maybe I take copy bar coefficient just so I can decompose without worrying about field of definition for the representations showing up in the site. So this has an action by the finite ideals of G. So I can decompose. So I can decompose the cohomology. So let's assume we understand the cohomology, decomposition into representations of G of AF. So this will become so H1. So pi of finite ideals, where pi is cohomological. So cohomological with respect to the trivial coefficient. Because we're looking at the representations showing in the cohomology of the Shimura variety. So maybe using the Matsushima formula from the previous talk by Tony and Michael, where so here I get where, okay, so here you get an additional sort of multiplicity space where you get, so let me write as the corresponding Galois representation, periodic Galois representation as rho pi. Actually, for some reason, I prefer to write as a dual. So dual. I should also take consideration of theta twist. Okay, that's theta twist. So theta twist. So same thing here. So here's the Galois representation. So attached to the automorphic representation. So this is I'm assuming this decomposition of cohomology. So of course in this full generality maybe we don't know yet, but in many cases we can. So we're going to use it. So in fact, this lies in a smaller space, so-called the Bloch-Kato Seymour group. So we're here. So this sort of lower index. Oops, let me see. This becomes maybe this one's better. So here, so this indicates the Bloch-Kato Seymour condition. So this means if you view this as if you view H1 as the space of extension of trivial of the Galois representation by the trivial Galois module, then this indicates this extension should be crystalline. Well, at least if my representation is crystalline at P itself. So there's a crystalline condition here. Anyway, so this is what the periodic height parent can be defined. So this map. So now I have this class. So I have a class defined by this by the sub Shimura variety given by the subgroup. So it's class. So now I can look at its image. So I can look at its image, and if I take one vector phi in pi f, I can evaluate, or maybe pi f dual control gradient. I can evaluate, so I can get a linear functional. So I get a linear functional goes from here to, well, so maybe I need everything to be QP bar coefficient now. So let's separately choose identification of complex number with QP bar, so that I'm viewing my phi as a linear functional. So I can, yes?
How do you know the class of the Shimura variety for H is cohomologically trivial?
Okay, so secretly I was cheating here, so I have to, okay, I have to subtract something, yeah.
Thank you.
Yeah, thanks. So here, then after that, I can apply this. So if I look at the image here, so it makes sense to talk about. So phi, apply phi here. So I get an element. So apply to this class. Well, maybe it's sort of cohomologically trivialized version. So this will be element in this tensor product. So it's actually in the Bloch-Kato Seymour group with the coefficient in the corresponding Galois representation with the correct theta twist. So this class will live in this finite dimensional vector space, the so-called Bloch-Kato Seymour group. So now you can plug in the periodic height parent. So now you can periodic height parent. Over Nicovar. So So which is a parent between this space so the theta twist is to guarantee that after you make the twist, this whole thing is of weight -1. So here, so you have this parent. Goes to, well, since I'm already extending, I have extended the coefficient to QP bar, so let's say I have QP bar value. So it makes sense to evaluate, so this parent, so the periodic height parent, I can evaluate. So those two classes, as I suggested last time, I prefer to write this class as an integration because just to make it look like Westbrook-Jay's formula. So this one, I will rewrite it as integral. So integral over phi. It's just a symbol. It's just sort of a notation for this sort of image of this class. So in this way, so here I apply the periodic height. So this will be. So this is well defined. I mean, except implicitly I have to make some choice to define this height parent, and also relies on the weight homology conjecture for this representation, which is sort of easier to check in comparison to to those conjectures you need to make the Benson-Bloch height parent. In a height parent with real value, the definition requires sort of more difficult to check more difficult conjectures. So this can be defined unconditionally, at least, if we assume the weight homology for this Galois representation. So then the conjecture can be, so this is the periodic version, so the AGGP conjecture here is that this height will be equal to, up to some simpler factor. So the derivative of a periodic L function. So let me state a little more carefully. Here let's assume pi is cohomological, say tempered. Automorph representation of G, which appears in the cohomology. And suppose I chose let's in pi finite part, and another vector in the deuce in the control gradient. So there's a periodic L function. At least when everything is when all the local representations above P are so-called ordinary. So let me assume sort of ordinarity condition. So phi v check. So at least say pi v. So this is sort of some technical condition. Maybe one can remove, but just for safety, let me assume it's ordinary in the sense of Hida theory. So the Hida's UP operator there is a vector where the Hida's UP operator acts by unit, by a periodic unit. So
can you explain the need for this condition?
which the ordinary? So actually, maybe in the Galois representation set, it's easier. So this means the Galois representation is triangular. So there's a filtration which is there's a full flag stabled by the Galois local Galois group above P.
No, but why do you need this?
Oh, why don't? Well, for a bunch of reasons. I mean, okay. One reason is, the periodic function in that case behave better. It's a measure rather than a distribution or So maybe, so actually, yeah, this is purely for safety. Maybe one doesn't need it. This conjecture probably exists if you formulate it correctly. Maybe it should extend to the non-ordinary case. So the second reason is what we can prove later on is only in the case of ordinary. So.
Also, the p-adic L function, almost all the p-adic L functions that have been constructed are ordinary. There are cases for small groups where they can construct more generally, but this is still under construction. A lot of work.
Right. So I mean, also there was a choice of Hodge filtration. In the ordinary case, there's a sort of distinguished choice. Otherwise, so actually to formulate the conjecture, I should also so the definition of p-adic function also involves some choices. Then there's also some choices. So hopefully you can match those two choices. But in the ordinary case, there's some distinguished choice which give you sort of a simpler situation. So this is the sort of the conjecture one can make. So this is a conjecture, sort of p-adic AGGP conjecture. So we should compare this with the Waz-Bourget's formula or the Ichino-Ikeda's formulation of a refinement of the Gangros-Prasad. So what I can mention some sort of so what do we know about this conjecture, the p-adic version? So this is well, let me just quickly mention. So this is joint work with Daniel Dizzini. So this is still work in progress. So we were hoping to finish like a few months ago, but we're still writing the paper. So roughly we can prove this p-adic version. So the p-adic version of AGGP. So this. So we can prove. So it holds. If P is good ordinary, so pi is P is good, so ordinary. But also more conditions on the local and more conditions on the local ramification. But roughly this means so pi. So the conditions. So let me ignore the condition at the split places. So the series condition is placed on the inert places. So pi. So the further condition is the following. So f prime over f needs to be unramified everywhere. So it's so in particular, some we don't have anything for the Q over the imaginary quadratic over rational numbers. So so we mentioned why this condition is needed, but actually slightly more more restrictive. So pi, so the local representation pi v for all inert places need to have a parahoric level. So is either unramified or has fixed vector by some maximal parahoric. So parahoric. So this means this has a fixed point. So it's a representation for all v inert in this extension. So that's essentially the condition we need. So here, let me just say that this condition maximal parahoric, and I can more precisely, this means either it has a hyperspatial level, or so in which case the representation is unramified, or it has fixed vector by certain compact open, so called KV inside G of FV, where KV is a stabilizer of certain so-called vertex lattice. So vertex lattice, which means a lattice. So let me just explain that. So here a lattice called lambda v. I mean, I should have done this for the product group, but anyway, it's for I'm just saying for each factor it need to be. So lambda v inside the local Hermitian space, which it's called a vertex lattice. So the terminology comes from Breuer-Tisse theory. So it should correspond to a vertex in a building. So this means this lattice is integral. So it belongs to it's contained in the dual lattice. So relative to your Hermitian form, and then but it's contained in but it's not too far from. So it's 1 over the uniformizer, local uniformizer. Times, so it's kind of almost, it's squeezed between this lattice and its translation by 1 over uniformizer. This means the dual lattice. This is actually a vector space over the residue field. So its dimension it will be called a type. So the dimension over the residue field will be called T, denoted by T or TV. Depends on V. It's called the type. Type of this lattice, vertex lattice. It's an integer between 0 and the dimension of the Hermitian space n. It should have the same parity as its parity is determined by the discriminant of the Hermitian space. So some nice representations which is next to unramified representation. So it's not too much ramified. Okay, so you will see why I need those conditions later on, and also why I have to assume this is unramified. And it's actually, you see that because I'm assuming this unramifiedness, I think this was already mentioned by maybe in earlier talks. If you have this unramified everywhere situation, particularly, actually, your Hermitian space must have some ramification. So you cannot have a situation where this is unramified and the lattice is actually self-dual for all inner places. There's no such kind of Hermitian space. Some local global obstruction there. So somehow you have to consider such sort of vertex lattice, such paraphoric level, in order to have actually global situation.
What p-adic L function is this for the p-adic Rankin-Selberg L function?
Oh yeah, this is the Rankin-Selberg for the base change. Oh, but for the cyclotomic direction, maybe this. Yeah, so the derivative is for the cyclotomic direction. So I only have to understand twist by finite order character.
But the p-adic L function, where you have a configuration of the weights for the u of v and the u of v prime for each.
Yeah,
and then those are not all constructed. Those are only constructed, I think, in one case. I think there are all the different branches for the weights depending on. I guess this is the one whose values are computed on the compact
So in this case, the Archimedean parameters are the parameters are actually determined by the Shimura variety, because I'm only in one of what you mentioned as the branches. So this is one of the many. It's one of the trivial with the trivial coefficient, right?
So that's the one that's realized
compact unitary group.
But who constructed this?
Actually, I mean, in our case, our proof can sort of reconstruct the PRDL function using a relative trace formula. But on the other hand, I believe it is constructed by Januszewski, or in maybe in even greater generality. But okay, I don't remember the full list of authors. I think there are quite a number of people who work on the PRDL function for Rankin-Silberg. But yeah, but either you can make use of their construction, but actually we have anyway in our proof we some sense we cannot use their the construction the known construction. So what I have to do is to redo everything using the relative trace formula. So that's partly also the reason ordinarity simplifies the situation. Right, but yeah, so I should have mentioned this. Yeah, this Archimedean parameters for such pi in this conjecture is a cohomological one for the trivial coefficient. So it's kind of the Jekyll-Lawrence transfer to compact unitary group is the trivial representation for the compact unitary group. So it's a generalization of the weight 2 condition in the case of GO2 to unitary group. All right. So that's pretty much the status of this conjecture. So what do we use to do this, to prove this? So this is what I want to talk about. So the relative trace formula. So RTF. So in this case, so like the proof of GGP or refined GGP conjecture, we compare two relative trace formula. One is sort of built in, so we already have our group G and H. So here on one hand, so sort of the geometric. Well, I guess maybe I call it. Wait, the word geometric side is used to refer to the orbital integral on a trace formula. So now I have to maybe call it, I don't know. So maybe arithmetic side, meaning arithmetic intersection. So arithmetic intersection. So here, by which I mean either the height pairing or one of the two alternatives I mentioned in the last talk, either the Gillet-Souley's intersection theory or the p-adic height. But actually, I mean, those two intersection theory, in some sense, essentially, well, at least locally, for the local heights, they essentially rely on the same type of computation. So here let's take a function f. So say Heck algebra or say compass supported function, and g of okay, it's unfortunate finite ideals. Maybe let me write a away from infinity. So have a function which you can in the proof of a GGP, you would produce a kernel function, or then you produce a trace formula identity. So here I start from here. So start from this guy. I have a correspondence. Let's write as RF. So this is a Heck correspondence. Correspondence. So I can talk about whatever height pairing or intersection pairing or p-adic height. So I can talk about, this cycle class or this algebra cycle, then project to so I can apply this pairing. So you can choose one of those pairing we mentioned earlier. So you make this definition. You call this. So it's called intersection. Int f. So this will be the analog. So this will be the analog of. So let me write over here. So this will be the analog of this integral. So the double integral over h bracket of the kernel function So this is the analog of this quantity. In fact, you can actually really interpret this. Well, in some sense, you can, or in some nice situation, you can interpret this as sort of naive intersection of. So I'm writing this bracket to indicate some intersection. Well, not a Shimura variety, but just this automorphic quotient. So inside G bracket. So here, so I leave you to kind of give an interpretation as some kind of naive intersection, like point-wise, like overlapping intersection two sets. Two subsets in your set with some multiplicity. Right? So that's why you see that there's a completely parallel situation here. Right, so from so the height, the intersection theory has the following property. So if the two cycles here are disjoint over generic fiber, so if they don't have any if their support over generic fiber are disjoint, then the height parent localize. So actually, so let's say f. So if f has a regular support, a regular semi-simple support. So this was a condition. For example, if you choose one place, you assume this local component has support in the regular semi-simple locus. Here, regular semi-simple in the relative sense, introduced in the earlier talk on the relative trace formula. Then you can show that actually the two algebra cycles are indeed disjoint over generic fiber. So you can actually localize the height. So this in this case, so int f localize as a sum of local height. So in the case of p-adic height, in the case of p-adic height parent, you only have to consider non-Archimedean places. So there's no Archimedean contribution in the case of p-adic height. So in the case of usual height parent with real value, you do have contribution from every place. So here now let me just focus on the local heights. So now let's fix one place. So fix one place.
So the BA is like the derivative.
Sorry?
So the sum of the places with this BA is like the derivative.
Related to, you mean each factor?
The sum.
Each summed? No, they don't. Only when they were combined together. But I have to talk about the other half of the comparison, right? So maybe later we'll have a better preparation to answer the question. So now let's fix one place. What happens is actually the split places are not interesting in the sense the intersection seems to be trivial always. I mean, so let's just focus on the inert place. So inert. This extension f prime over f. All right, so well, maybe also there's also ramified, right? But one issue I mentioned last time already was to compute the local height. Actually, you have to bring in some integral model. So the integral model, which you want the integral model to be regular. So there are only very kind of few cases you can produce a regular integral model for Shimura variety, which which of such type for such signature. So I think this was mentioned in Chao Li's talk, where he already listed, in some sense, all the cases we know. You have a regular integral model, which are the following. So if you have inert place, which means so locally this extension is unramified, so you can produce, you can impose. I mean, you can consider the level structure attached to what I wrote here. Those sort of parahoric, maximal parahoric attached to vertex lattices. So in this case, you can produce integral model which are regular. In fact, actually, they are even strictly semi-stable, so very desirable to have to do intersection theory. The other case was also mentioned in Chao Li's talk, which is if this place is not inert but ramified. For example, if you have a quadratic extension of Q, there will be necessary ramification, right? So you are forced to impose some ramification, you're forced to be in some ramified situation. So there you also have some level structure where you have you get a regular integral model for the unitary Shimura variety. So here I'm gonna sort of use the integral model introduced in Chao Li's talk. So I'm kind of just pretend we already have those integral model and the desired properties. So you can refer to his slides and his lecture notes. So what makes different? I mean, what makes me assume only inert is that. So for the ramified case, so I will state some So what you can make all this definition is it's okay. You have this intersection numbers defined, but what is missing is in the side of L function. So later on we introduce other half. So this comparison we only know for the case of inert with the maximal parahoric level, where in the ramified case, in the ramified quadratic extension case, we don't know how to prove yet. So anyway, so here if you have inert place, I can produce integral model. So again, this was done by really not considering this unitary group, but consider some kind of closed relative, right? By adding some center, so making a GU, but not exactly semi-unitary group of those guys. Some kind of modification of the unitary group. Then you have some nice integral model, but the price you pay is to extend your field of definition to some larger, possibly larger field. So, but anyways, I will sort of suppress those issues. So as if I'm working with this type of Shimura varieties. But anyway, so I have integral model. Let me write. So let's say in those and maximal. Well, let me just do the hyperspecial case. So lambda v is self-dual lattice. So I will see it later on. I will remark later on what's going on if you have some long self-dual but still vertex lattice. Self-dual lattice. V over V. So in this case. So I have the Shimura variety. In fact, for each of those two factors. So anyway, so you make a Shimura variety for the product. So let me call the integral model M. So let's only consider the local. So the local. So this is over. Again, I'm ignoring the issue of you have to actually really consider a larger field extension of f prime. So this is the integral model, which is actually smooth. So smooth. Since we're not in the case of Q, so this is actually also proper. So now, so let's also assume FV. So here, so FV is the stabilizer KV. So really, it's the product of two unitary group. So here, so for each, so this simple, it's a unit of the Hecke algebra, the spherical Hecke algebra. So then I have the cycle as well. So in this case, int FV can be interpreted as, so this in this case, sort of by definition, it is log. So there's a log factor QV, the residue cardinality times a Euler characteristic. So chi. So I'm just writing down the definition, in the sense of. So you write. So I have this. Okay, let me write it. So the cycle. Let me write as mg, mh. The cycle is called mh. So those are the integral models. So in this case, really, so the intersection number is this sort of derived tensor product of so over the big mg, and then translate by RF, Hecke correspondence. So it's this sort of the length over the Euler Poincare characteristic. So here, so this is really the definition of the local height in the unramified, in the good reduction case. So what happened is this regular support condition guarantee that the physical, the scheme theoretical intersection of the two cycles here are actually supported on the special fiber, because I said earlier that they have no intersection in the generic fiber, right? So really, the scheme theoretical intersection is a proper scheme on the support on the special fiber. Let me put the place V just to localize this. So you get some complex of coherent sheaf supporting on the proper scheme in the special fiber, so you can compute the coherent cohomology, take the Euler Poincare characteristic. So that is the intersection. So if f, my Hecke function f over there, let's assume f has a sort of rational coefficient. Then you see that this actually, well, this lies in, Q, or if whatever the value of the function f is, you put over here. So it's really Q of log Q, right? So it has a value over there. So I want to mention that in the p-adic height case, it's almost the same, except you have to understand, or you have to reinterpret, log Q as a p-adic log Q. Which makes sense, right? As long as P is different from the residue characteristic, right? So in that case, you will consider this as p-adic log of Q, which has a value in QP. So in some sense, that's why we're using the same ingredient locally for the height, at least away from P. Right, so this is the local intersection.
Is it obvious that this is zero almost everywhere?
This is zero almost everywhere. Yes, it is clear, because if I drop this place, those two schemes, well, they're all proper, so the intersection is a finite type. It has only support over finite many primes. It has to be finite type here. I mean, it has no intersection. It has no points over generic fiber. So that's what a guarantee. A priori, this only has contribution from finite many primes.
The derivative of the complex L function is the sum of over places of infinitely many terms of which only finitely many vanish. What about the derivative of the p-adic function? Why do you have how do you get a sum over terms?
No, I didn't understand your question. Can you? Yeah.
So in Gross Zagier formula and other generalizations, height pairing is the sum of local terms.
Right.
And the derivative is also a sum of local terms. But that's the complex L function. But how is the derivative of the p-adic L function the sum of local terms?
Actually, the derivative of an L function is defined by, I mean, after you take take analytic continuation, right? It's not really on the nose you can take a derivative. So what happens here, I think you always have, I mean, like here, really, for given f, there should be only finite many places on the right-hand side. Of course, when you vary f, you potentially have all the places involved. I think the same for the p-adic.
I can see the structure of the proof for the complex L function because the derivative is the sum of derivatives of Eisenstein series. So there are infinitely many places, I mean, they can include the program.
Yeah.
There are infinitely many contributions locally, and there are infinitely many contributions locally to the Neuronte height. But for the p-adic,
should be the same.
But how do you get? How about the derivative of the p-adic L function? Why does the derivative of the p-adic L function? Why is it a sum of local terms?
So maybe we should leave that to the Q&A. I don't have a short answer. Actually, I don't understand the question. So maybe we should postpone it.
I'll ask exactly the same question.
Okay. All right. So okay. So that's the intersection side. So one can so now I can try to localize the question. I mean, even further localize this. This seems to be localized because I'm considering one place, but it's not really purely local in the sense of local Shimura variety, because here I still have a global. I mean, still have a global Shimura variety, right? Just base change, just taking base change of global Shimura variety to the completion at one place. So I really want to localize in the sense of, I want to get something on a local Shimura variety. So here I'm going to bring in the uniformization. I should also mention what happens here. In fact, the scheme theoretic intersection has support only in the the basic locus. In the case of rational numbers over and quadratic extension, you really get supersingular locus. So I only have to consider the formal neighborhood of the total space, formal completion along the basic locus of the spatial fiber. So that has a nice description using. I can reduce to local. So local setup. So the local Shimura variety, or in this case, really the Rockwell zinc space. But maybe there's a little subtlety here. I really want to have something over integers rather than the generic fiber. So I want to have something some integral model. So here, so you can use the uniformization. So the Rockwell zinc. In this case, so uniformization. So there is so if you take the formal completion, so of the total Shimura variety, okay, let's actually base change to the maximal aromatic extension. So let's call it FV for AV. So here, this is something right over here. So V is a So this is the maximum unramified completion of maximum unramified extension. Completion. So if you formal complete at the basic locus, so this has a description in terms of local Shimura variety, which I believe was discussed already in Jared Weinstein's talk, maybe also other talks. So let me call it n, write as n. So n at v, so times g of finite ideals away from v. So take the compact subgroup away from v. So then you take the quotient by g. Let me write out g bracket v. Okay, I will explain what this is. So where g bracket v is the new ingredient. So here, so this is the local RZ space, or it's a formal scheme defined over integers. So this guy is the same group but attached to so-called the nearby Hermitian space. So I think Chow Li's talk introduced the nearby attached to nearby Hermitian space. So which means it's the same Hermitian space at all places as we started with, except at v and infinity. So now it will be all. So this Hermitian space, nearby Hermitian space, will be positive definite for all Archimedean places. But at v, you switch to a different one. So here there's a sort of change of local invariance over the Hermitian space, exactly at two places. So using this description, and by the sort of, if you remember how we arrived from here to orbital integral, right? So if you think about how we get an orbital integral from this integration of a kernel function, you will believe immediately that this intersection number will be something like orbital integral. Well, except there's some modification to be made above v, because you see here it looks like the same as this automorphic quotient away from v, right? It's away from identical points divided by something here, right? Right. So let me just write it without giving you the full sort of detail of proof. So I'm gonna write over here. Just continue. Wait, where is the eraser? Oh, it's down there. Okay. So the output will be, so there is a log QV. So, okay, will be sum over orbits. But now the orbits is relative to this new group, G bracket V. So this is a new group. So this notation, G bracket V, means the unitary group attached to this new Hermitian space. So we'll be orbit, so let's call it G, orbits on, oh, sorry. So the regular semi-simple orbits. Then I have orbital integral. So orbital integral for the function away from V. And some I write as into V, so this is local quantity G. So this will be intersection. You define the intersection number on the local Shimura variety, following the same type of consideration. So, but now it depends on a element G lies in this group, which acts on this local Shimura variety by changing the sort of quasi-isogeny, by changing the rigidification. So you get this kind of expression. So the only difference is you have kind of some new information out of V, which is sort of local, which is intersection number on the local Shimura variety. Okay, good. So that finished my geometric side. I mean arithmetic intersection side. So now I'm gonna bring in the bring down this one. Oh, where is the other one? Ah, it's behind.
Is the gamma is this formula actually G?
Oh yeah, right. Thank you. Yeah, I was debating whether to use gamma or G, so then I used both. Yeah, I want to reserve gamma for the GLN side. So. Great. This one. So now I'm gonna move to the L function side. I mean, as you see, we have to compare the intersection theory with the L derivative of L function. So so this is done by construction of Zagier and Rallis. So I first learned this construction from a talk given by Zagier. So Zagier gave a talk in, I believe, in 2007, in a conference at Columbia. So this at least exists before, at least 2007 or before that. So at that time, so as a graduate student, actually I didn't understand any word of Zagier's talk. For one reason, actually, this is maybe related to one remark made by Matt Emerton in his talk. He said, at his time of graduate school, students in number theory mostly work with GO2, right? Modular form. Maybe except Dick students, the Gross students, they have more bigger group of automorphic forms. So actually, the same thing happened. I mean, I think it's the same even in when I was in graduate school, which was maybe 10 years or 15 years later. So I was, as same as most graduate students in number theory, mostly we consider GO2. But Zagier's talk was on the unitary group of arbitrary rank. So I just, like you, I just take notes. I took notes, like most of you here. Then when you go home, the chance of looking at it again is infinitesimally small, right? so that's the same thing happened. So 2007.
Graduate students in France were working with bigger groups.
But that's, well, I think same at Columbia. Students of Zagier work with a bigger group. So students of Wei Zhang work with GO2 at 2007. So the situation changed only 1 year later when I read actually a paper by Kudler-Rappaport when they consider introduced in Chao Li's talk when they formulated the Kudler-Rappaport conjecture. So they had to consider the Shimura variety attached to unitary group of arbitrary rank. So only at that time, which was like 1.5 years afterward, so I realized maybe Zagier's talk was exactly about something similar in the GGP, in the arithmetic GGP situation. So then I start to run back to my home. My room. I start to search for my notebook, which was underneath somewhere. So after 1 year, you wouldn't even know where to find it. So fortunately, actually, I found this my notes for Zagier's talk. So that was kind of before Zagier's paper was kind of I think was published much later. So I actually had my notes available. So I started work on this comparison from there. So the notes might be useful. So, even though. So here, so we know that, okay, I think this must have been probably already show up earlier in summer school. So here you consider G prime being GON, GON over F prime times GON minus 1. And H1 prime. So I'm just gonna write this group without really seeing too much. GON minus 1, F prime, so the diagonal embedding. And then, so we know the H1 prime automorphically pairs integral will give you a Rankin-Selberg L function. So H2 prime will be GL N over F, the base field. Yeah, I should write this as maybe by restriction of scalar. So it's a group over F. So restriction of scalar. So N minus 1 over F. So I have two subgroups. Then you produce this integral kernel function, so called F prime, where F prime is it's a function complex of ordered G of prime. So over H1 bracket H2 bracket so H1 H2. Right, so now you can produce Rankin-Selberg L function by take determinant of H1, then take S power, which is complex number, complex parameter. Then you take some quadratic character of H2. So then you take this integral. So let's call it J F prime S. So the spectral side will give you Rankin-Selberg L function. So you take the geometric side. So this will have at least for the good orbits called gamma. So it will be orbits. So regular semi-simple. Modulo the translation by the two subgroups. So regular semi-simple orbits. So now you have orbital integral gamma F prime with S variable, at least for the good orbits. So so J S. So the spectral side, spectral decomposition. So you take the spectral decomposition, you get pi. Well, capital pi, so automorphic representation of GL, G prime. So at least for the cuspidal ones, you get L function, Rankin-Selberg L function. So Rankin-Selberg. S variable times some local quantity, sometimes so local character. for each place. So if you look at the two formula over there and down there, so there's a natural hope to have a termwise equality, right? At least, well, if you care about derivative, let's take a derivative. So hopefully the derivative will have you get an equality of each individual term. So then you see that the question will be, well, so the new question compared to proving the central value version. So there was the usual AGGP conjecture, right? About comparing central value wave function. So where you have to prove there is a way of comparing the usual orbital integral. So in this side you just take the value s equal to 0. So you hope, well, this was probably also discussed in Yannis's talk, right? So abstractly you want to compare all the possible orbital integrals. So you want to see that the space, so orb of gamma, well, so let's say in the good cases, say 1 of kV is supposed to be, so this is the value when s equal to 0, should equal to our orbital integral of g 1 over kV. Well, I shouldn't use same kV prime to indicate it's on the g prime side on the group of g o n. So as long as the orbits gamma and delta, g and gamma have the same invariance in the geometrical quotient. So in this case, the two RTF, they have the same geometrical quotient, so you can match orbits using the invariance. So this is the fundamental lemma. So this is the relevant fundamental lemma. So here, well, you see that one thing. This is the one thing you need. Another thing is to, let me get rid of this one. So then, you have to also compare the orbital integrals for more general test functions. But okay, let me just focus on the new information you need. So you need, let's call 1 prime. So this means, so the new information will be at the place above, so here above V. So arithmetic, so the version of fundamental lemma. This means I take the derivative orb gamma prime equal to the intersection number of GV. So this was defined using the local Shimura variety. So whenever gamma matches G, although I mean those two G really lie they lie in different unitary group. Here G lies in the quasi-split unitary group. Here G will be in the sort of non-quasi the unitary group attached to the so-called nearby Hermitian space. So it's not really two. I mean, it's not like you have two statements for the same gamma. Kind of the disjoint sets. Those two cases, the orbits gamma, they lie in disjoint sets of orbits. So there's no. I mean, really, there's no overlap for those two statements. Right. So okay. So that's what. So the first statement was proved by Zhiwei Yun and Julia Gordon, using the strategy of Bauchow's geometric strategy. So there's also more recent proof by Raphael using more harmonic analysis, more of local trace formula, inductive proof. So here the arithmetic fundamental lemma. So you see that the ingredients to match up those two things is the theorem. So for AFL, well, okay. So I prove this when the base field is QP, but then with the Mihaly, so we extend to general periodic fields, but we need to assume the residue characteristic is big. Like maybe bigger than n than the dimension of Hermitian space. So more recently, so Wei Zhang, so my graduate student, so he actually managed to remove this big residue characteristic condition. So now you only have to assume P is odd. So okay, let's still assume the prime P residue characteristic is odd. Characteristic of K of the residue field. Is odd. So then this actually, if it holds, so in this generality, so that's one sort of one key ingredient to the result I was stating for the periodic height. So then I was only talking about hyperspecial case. So for the non-hyperspecial case,
but what is periodic here?
What is the periodic?
Because you said periodic, this is the ingredient for periodic height. This is
right.
Michael's question from earlier.
Okay, so here the residue characteristic QV is supposed to be the periodic is the prime P is different from the residue characteristic Q here. So
the question is, what's the relation to this int VG and the periodic height?
No. So
and what's the relation on the other side to the periodic L function?
So I can answer maybe the height question. So the int. So if you interpret my int in that blackboard as the periodic height, then the decomposition into local heights, which is over there. So this is so you still have this localization. Localized to each place. But then I will be discussing. So what I said here only applies to places away from P. So this is only about, it's the local height for the periodic height away from P, where you interpret this log number, right, log Q, as a periodic log. So log P of Q, where Q is of course different from P. It's not the power of P, it's the power of a prime different from P.
So you do the generalized comparison with 2P bar coefficients.
Right. Then but everything is actually really, it's over a number field.
What's the relation between the left-hand side of the arithmetic fundamental lemma and the derivative of the periodic L function?
I see. That's why I said I only answer this height side. So the periodic L function side, it's more involved. So I cannot answer that side because, so here is only for the complex periodic, complex L function.
You can answer it, but you can't answer it maybe in the available time.
Right. Okay, so forgive me to be inconsistent. There I was kind of allowing both cases, the Archimedean height and the periodic height. Here I really only focus on the complex L function. So, okay, I was also, if you look at my result, I was saying I also allow vertex lattices. So in that case, you have a regular integral model for each individual Shimura variety. When you take this product, so actually the product does not have to be regular anymore, right? So there's a resolution of a singularity process being introduced. So that's a work of Wei Zhang. So he introduced a resolution for the product singularity, but then he has actually carry out, the sort of computation for the also for this, to look at the strict transform of the cycle, then related to the orbital integral. So anyway, so that's his thesis, where he can extend this statement to the case with ramification. So with ramification of this type, of the type given by maximal power Horrick in an inert place. And so in last, so that more or less explains how we, I cannot explain the place above P. Just as the same situation happens for the complex L function, I cannot explain the situation at infinity. So there's Archimedean computation, which is, the Archimedean height I mentioned yesterday is actually defined without any kind of is unconditionally defined. You have a well-defined height parent for the Archimedean height, for the Archimedean place. But we don't know how to prove the corresponding comparison between derivative of orbital integral for the Archimedean place and the local heights at infinity. So that's definitely, so yeah, maybe I can use the last 5 minutes to indicate what is not known and desirable to have. But hopefully I have explained, by using this statement plus Wei Zhang's generalization to make some more power heroic, I actually plus unexplained p-adic, the place above p, which is the work with Daniel Dizzini, we will be able to prove a p-adic version of AGGP conjecture. So for the last 4 minutes now, so let me talk about, let me indicate some sort of questions. So first question would be for the Archimedean place. This seems to be still difficult. So the Archimedean height. Questions. So why is Archimedean height? So this we don't know how. We don't have a good understanding. So in fact, actually, this has something to do with what so far our summer school hasn't had anything to do with Deline's paper on the special value of L function in the last Corvallis. So maybe it's time we can also try to make some conjecture which is related to Archimedean height. So here, Deline's Corvallis paper actually formulate a kind of unifying conjecture for the special value of L function, at least of motivic origin. So what happened to, maybe this question came up earlier, what happened to sort of higher derivative, right? So I think Kontsevich Zagier observed, so in their paper, so they defined a algebra of so-called periods. So they have, so this roughly this is defined as, I think Deline's paper mostly about the pure periods, so pure Hodge structure. So you can define periods. Here they are a lot more kind of general integral. So you can integral a algebraic differential, so defined over algebraic number fields, over homological cycles, but with you can even consider relative cohomology. So it might have a boundary, but the boundary needs to be defined over number fields. So those are so this includes all the basically most interesting numbers from the perspective of special value of L function. But they also observe, if you look at, say, elliptical curve, so A is the elliptical curve. Then the leading coefficient, say R is the order, if R is the order of vanishing. So this is not in the Deline's consideration, because I think Deline's conjecture was about the value, not the derivative or higher derivative. So if you look at the derivative here in the center, so they observe if you assume BSD. So by BSD, this actually implies, Birch-Snell direct conjecture actually implies this is actually a series. So it's actually in their algebra, in the Kontsevich Zagier. So roughly they just prove the usual periods times the regulator of height parent is actually a periods. I mean, this is not surprising in some sense, because the height parent essentially measures some complexity of a mixed Hodge structure. So so the Archimedean height really measures some mixed Hodge structure. How complicated your mixed Hodge structure is. So it's kind of some mixed periods. Periods attached to mixed Hodge structure. Well, can we actually speculate? I don't know if we should call it conjecture or maybe question. Question. Should we expect? Well, say, any the leading coefficient. So this is the leading. R is the order of vanishing. It's kind of, well, concretely I can do for AGGP, right? So, but in general, can we expect the leading coefficient of any regular algebraic cohomologic automorphic form, the attached L function, the central value, the leading term? Should this be appearance in the conservative Zagier sense? Okay, that's for the leading coefficient. For the non-leading coefficient, there's even less is known, but they also observed Comet's conjecture implies for certain RTL function, the non-leading coefficient, actually they are also closely related to periods, but they're not a periods, but logarithm of periods. So I wonder whether one should, whether one can define a bigger algebra than conservative Zagier, which include even the non-leading coefficient. So one reason of such belief is in the function field case. So my work with Zhi Wei Yun. So we actually prove that there's no difference between leading coefficient and non-leading coefficient. You don't quite see the difference. Right? So somehow leading coefficient might be actually misleading. So there's no difference between non-leading or leading. As long as they are second derivative, they should behave like the same. So anyway, so that's purely speculative. So that's one question. So second question will be for the non-Archimedean height with deeper level. Non-Archimedean height, local height. So here we should have more sort of arithmetic version of transfer conjecture in the sense of comparing the derivative of orbital integral with intersection number of local Shimura variety, but with deeper level. So there's not a good understanding here either. So one more quickly. So there's also degenerate term. Everything here in this talk was about the regular semi-simple orbits, but there's also non-regular semi-simple orbits. So on one hand, Pierre Henry and Zidor, they already defined the orbital integral, even in the degenerate case. Right? They have a good definition for the orbital integral, but we don't have a good understanding for the intersection theory. So far, I was assuming under this sort of blanket assumption that my test function f was regularly supported. So this is definitely something we do not understand. So, but this should also be interesting because, in some sense, the known case of Comet's conjecture should be viewed as a degenerate term in the Kudlar-Rappaport conjecture or Kudlar's program. So here, what I wonder what play the role of degenerate, those sort of long regular semi-simple orbits. So what it should contribute from the arithmetic intersection theory. So finally, yeah.
Is that related to Tony's comment about derived intersection?
Right, partly related, yeah, I think. Yeah. But in this sort of setting of GGP setting, I think Tony was more in the Kudlar-Rappaport setting. So finally, well, there's also issue of beyond the Shimura variety. So here, I want to mention, so beyond the Shimura variety, so here, the cases I introduce for the GGP conjecture, where I have codimension 1 case here. So this Hermitian space is of codimension 1. So this group is reductive. So there's also conjecture of GGP, which involve unipotent, non-reductive subgroup H. So that's what we call, the general Bessel model. So here there's no global Shimura variety which can explain which can be used to formulate a Gross Zagier type conjecture. But locally you do actually. So because you do have local Shimura variety, greater generality than the global. So actually formulate a generalization of arithmetic fundamental lemma involving local space which does not seem to globalize. I mean, okay, they still show up in the global Shimura variety, but you cannot get a analog of what I wrote, in this board hidden behind, so something which cannot be globalized. So of course, this means we have to wait for the invention of new Shimura variety, global Shimura variety, an analog of Shimura variety for the greater generality. But even locally, there's something. So that seems to be very difficult. But even locally, so locally, so there are cases which involve exceptional groups. For example, exceptional groups which definitely Roper-Zinker's definition do not apply, where you have to use the new modular space of mixed characteristic Shidokan, local Shidokan of shots, and so in that case, for example, you can consider E7. I think E7 has some spherical subvariety where I checked seems to be perfectly suitable for the same type of consideration. But where you do not have a kind of simple formal scheme, or you don't have good integral model to define intersection theory. So there is you have this local Shimura variety probably being a diamond or some V sheaf, but I wonder if one can make an intersection theoretical definition, then you have a well-defined arithmetic fundamental lemma locally, but globally we don't. Let's forget about global situation. So, right, I'm way over time already. So let me stop at this point, and thank you for your attention.